Hello, gentlemen. So I'm going to be going through what we did in our last class lecture, so earlier this week on Monday, Tuesday, and then what we're covering on Wednesday and Thursday for your benefit for the test that is on Friday for my A day, Monday for my B day. So to recap, what are electrons? Electrons, they're outside the nucleus, they're negatively charged, and they have a very, very small mass. It's considered negligible because it's not as big, and it's not really affecting our atom's mass in any way. So we can consider our electron mass to be equal to 0 just to make it a little bit easier. Now, electrons are really important in something that we call bonding. Bonding is very important, and we'll kind of cover that more in our next unit, but it's important that you know when we bond two elements, so like my water, H2O, the bonding is happening in the electrons. And then I have a video about it. Now, what's important to know is we have different energy levels when we're looking at our atom. Electrons in the cloud exist at different distances from the nucleus. That's what our energy level definition is. They correspond to the period numbers on the periodic table. As you recall, periods are horizontal. And so it's going to correspond with my 1, 2, 3, 4, 5, 6, 7 going down. Now, in the Bohr model, these are depicted as perfect circles. However, that is not true for our energy levels. There are actually a lot of different shapes, and they're not perfect circles. But we draw them that way because it's just a little bit easier to see it. Now, what's important for you to know is that there's a limit on how many electrons can exist on each energy level. On the first energy level, it holds a maximum of 2 electrons. On the second energy level, it holds a maximum of 8. And on the third energy level, we also hold a maximum of 8. Once we get to the fourth energy level, we can hold 16. However, I will not be asking you to draw a Bohr model that surpasses an energy level of 3. So it's important that you know my first energy level only holds 2, and the next two after can hold a max of 8 electrons. Now, we associate these with the Bohr model. We can inaccurately draw the relative location of the electrons for an atom with the Bohr model. The Bohr model is old. We're actually in what we call the quantum model of the atom right now. It's very cool, very fancy, but it's very difficult to draw. And so we use the Bohr model. So other examples for you with our Bohr model is right here. Now, let's practice drawing a Bohr model. We did this in class, and so I am just going to give you the answers. However, if you'd like to try this on your own, we have magnesium and a fluorine with a -1 charge. I get the 2 types of Bohr models that look like these. Now, what you need to understand is that the next thing we have is valence electrons. And using these energy levels, we can tell what our valence electron is and how many based on where they're located. And so valence electrons are located on the outermost energy level. What's important about them is that these are available for reactions because they can move and they can create those bonds. So valence electrons are probably our most important electrons compared to my inner ones. Not saying those ones are not as important, it's just that valence electrons have a bigger job. So valence electrons, how many valence electrons does fluorine have? So fluorine, you think, oh, it has 9. The first ring can hold 2, so I can have up to 7 valence electrons in my second ring. Magnesium, I have 12. So my first ring holds 2, my second ring holds 8, so I have 10. So then my last ring will have 2. Valence electrons for carbon. Carbon has 6. The first ring holds 2. So that means the last ring has to hold 4. And sulfur is a 16. First ring holds 2. Second ring holds 8. So the last ring can hold 6. Do you notice a pattern when we go through this? Excuse me. Cool. The pattern is that our main group elements are the number of valence electrons. So the Roman numeral that is above your groups, remember your groups are your verticals, correspond with our number of valence electrons for each element of that group. So let me scoot myself up. Our first one has 1, our second one has 2. We don't worry about the transition metals, so we go here where this one has 3. Group 14 has 4, group 15 has 5, group 16 has 6, 17 has 7, and our noble gases have 8. Helium being the exception with 2 valence electrons, but it's considered full, hence why it's there. Now, the next thing we have to talk about is the octet rule. So elements, when they are not just like hanging out, they want to have what we call 8 valence electrons. The reason they want to have these 8 valence electrons, which is considered our noble gas, because noble gases have 8 naturally, is that it means that they're stable, because they don't have to worry about giving up or taking electrons to reach this. So they can just say, we're stable, we don't have to worry about anything. So my question is which group of atoms has 8 valence electrons? The answer is noble gases, so they naturally have it. So now the important part is that they want to become stable, and it's how do you determine that they want to be stable, and how can they do that? So when I look at sodium on my periodic table, sodium has 11 electrons. Now that means it has 1 valence electron because it's in group 1. It wants 8. So you need to decide, is it easier to lose 1 electron and bump down to 10, or is it easier to gain 7 electrons and bump up to 18? In this case, gaining a lot is a lot of work, but getting rid of 1, that's a lot easier. So I'm going to lose 1 electron so I can get up to my 8 valence electrons by having a sodium with now a positive 1 charge. Chlorine is number 17 on our periodic table, and so for this case, I want to get to 8, and chlorine naturally has, I want to say 7 electrons in the valence electron shell. So for it has to decide, do I want to lose 7 or gain 1? In this case, it wants to gain 1. That is a lot easier to achieve. Beryllium is naturally 4, so for it to gain or lose electrons to become stable, in this case, it can consider going down to 2 or hopping up to 8. So it can either gain 6 or lose 2. It is a lot easier to lose 2, to have 2 in my first ring, which is considered stable because that first ring is full. Sulfur is 16, so for it is easier to gain 2. And for argon, it is 18, meaning it has naturally 8 valence electrons, so it doesn't have to worry about losing or gaining, which is really cool. Okay, now we're going to talk about our periodic table trends. This is important. We cover this mainly in class on before the test, and then we do a lot of examples in class for you. It does that. So this one, it should say atomic radius, however, it did not come up for some reason, and I denote this with AR. The definition for atomic radius is that it's distance from the nucleus to the outermost valence electron. I will make sure these slides are updated on Canvas for you with the name, because I don't get why it's not coming up. Now, atomic radius, what I'm pretty much saying is that I have more rings away from my nucleus. So look at this image here. As I move down my group 1, I have a higher atomic radius. Now it's important to note the atomic size increases as you move down, but as you move left to right, it decreases. Now when I'm going down, my atomic radius increases, and the reason why is there's more energy levels, so the radius increases, which feels very self-explanatory. However, when I'm moving across the period, my atomic radius decreases. The reason being is that I'm adding more protons to my nucleus, and so my ring number is the same throughout my entire period. However, my nucleus is naturally positive, my electrons are negative, so they attract. Meaning that if I have a more positive nucleus, my electrons are going to get as close as it can to it, resulting in the atomic radius decreasing with the increase in protons because it is an increase in a positive charge. Next thing that we're going to talk about is ionization energy. Wow, this one came up. And I'm going to denote that with IE. It's a little bit easier instead of writing ionization energy. The definition for this is it's the amount of energy it takes to remove an electron from an atom. Okay, so when I'm moving down my periodic table, down in my groups or my families, it is easier to take away an electron, so the ionization energy decreases. The reason why is because I have more rings, and so it's farther away from my positive nucleus. So it's pretty much that saying, like, if I was socially distanced and I had a pencil and I'm holding it between my two fingers, it's easier for you to come and take that pencil from me because it's farther away from me. Now, I'm the nucleus, the pencil is my electron, so it's farther away. I'm not, like, I can't, like, whip my arm back really fast, so it's easier for you to take it when it's between my two fingers. So think about it like that. Whereas if I am smaller, so I have lithium, for example, and I'm holding the pencil here where it's closer to me, it's a lot harder for you to take it because I can drag or draw in my electrons a lot easier because I have a stronger pull because they're closer. It is a little bit, we're going to practice it in class. So if you remember, think about my marker example. Now, across the periodic table, moving left to right, the ionization energy increases. The reason being is that I'm more positive in my nucleus, so I already have a small atomic radius and I'm hugging them in, so it's a lot harder for you to take away when I'm hugging them in. So if my marker was here and I'm holding it, you could probably take this, but if my marker is here and I'm holding it, you're probably not going to be able to take it as easily. So it's kind of that idea where that atomic radius is decreased, like it's very small, but it's because the electrons are attracted to that really strong magnet or my nucleus in the center. Now that's all I have for you. You should work on the review guide as your homework. I did post the review key for the station, so that way you can use it as a reference. However, you should answer the additional questions and make sure that your review guide is filled out with any notes or following information that you will have. I hope you have a wonderful day, but please email me if you have any questions. Bye.